pleasure for. The topic is performance-based design for earthquake-induced liquefaction. I have application to offshore energy structures. Two of them I've chosen, offshore wind and subsea structures. The paper itself is co-authored by myself and my colleague at Hao Yuan Liu at Norwegian Geotechnical Institute. I myself am now at Norconsut and at the same time NTNU. Basically, as I said, I'm going to touch on two topics, offshore wind, application of liquefaction, and subsea structures, both related to energy. But I thought to show some images from offshore wind. They are generally more interesting recently. Basically, I start with some introduction. The introduction is actually on this page that, especially with offshore wind, it has been a major development in this field, as you can see, all the way from 1990s and now to 2025. What is interesting is that actually the development has been even faster than the prospect. That this image is from 2017, and it says that in 2025 we will reach 13 to 15 megawatt. We're almost there now, not every project. This shows the sheer immense size of these structures. The foundations are very different types. Monopile here, excuse me, and this is like jackets. Usually the part just below the tower is like shown in red, yellow, I'm sorry. And this is the same one, this is the same. So this is like the transition piece and the structure comes on top here. So then I will go to design issues related to liquefaction, some modeling issues initial in my, actually I'm going to present you the result of the last 4 years of studying this subject. So I start with the early part, the first 2 years with using the classical sunny sand, and then I will move to the last 2 years with the more advanced version of sunny sand. And I thought it's good to build up on this one and show how the evolution of the results and the research has been. Then I will show you some results for monopiles, subsea structures. I will then move to the features of the more recent developments, sunny sand, memory surface version. Then I will show applications to offshore wind and subsea facilities. I will talk about the differences in the two sunny sand versions, and I will end up with some engineering observations. Let me start with background, offshore wind structures. I start with that one, and then I have a discussion on subsea structures. They have challenges, actually, a little bit shown on this sketch on the right side, that is still under rapid expansion. It is predicted in already 2019 that by 2050, we will have something like 400 or so gigawatt capacity of installed energy in offshore wind. This is just to give you an idea with the typical today's capacity. It's about 40,000 wind turbines. This is immense. I think in view of all the other under predictions and the focus on energy recently, this will be exceeded by the time we get to 2050. There are challenges, complex environmental conditions. You have wind, you have wave, and you have, of course, many load cycles, millions and millions of load cycles, dynamically sensitive structures they are. Fatigue is an issue. And of course, for us, geotechnical earthquake engineers, strict performance criteria with respect to the deformation of these structures. And this shows, like, gives you a picture of the type of loading. It's just the special type. This is the wake behind some of these wind turbines in an early morning. The ice particles, actually fog, have been crystallized and gives a picture of what the wake looks like. and the other wind turbines. But of course, for us, earthquake in seismic areas, very generally speaking, very much we could say offshore wind turbines are generally not sensitive to earthquake shaking per se. However, it's very general statement. However, one of the challenges in liquefaction, and the reason is that the natural period of these structures are typically 3 to 4 seconds, and earthquake is not the number one concern. Just a little overview of the challenges and differences between offshore wind and other structures. For design earthquake 475-year, typically foundations of offshore wind should not experience permanent tilt. This is very strict compared to other structures. Earthquake is considered simultaneously with other environmental loads, wind and wave, as opposed to ordinary structures. We do not usually combine them. There is very little damping in tower structure, as low as 0.5 to 1%, as opposed to typical earthquake design up to 5%. Vertical shaking usually is not a concern in ordinary structures. In offshore wind, vertical shaking could be a major concern. Kinematic pile interaction is usually not a concern in ordinary structure. However, if you think about these two types, especially kinematic interaction because of the rotation, could be an issue. But of course, here I'm going today I'm going to focus on liquefaction, which has not been adequately studied for these large diameter turbines, monopiles for turbines, and requires rigorous performance-based design solutions to predict the deformation. My own interest in the subject was triggered by the study some 4 or 5 years back at the University of Colorado, very interesting centrifuge study together with performed by Professor Dashti and her colleagues, and several studies came out. One of them is the report paper by Ramirez et al. In 2018 that evaluated different liquefaction models, and it was a good collaboration between 3 universities, 2 constitutive models and 2 numerical codes. Basically, this is a picture of the centrifuge box and good, well monitored, high quality testing, different constitutive models, sunny sand, and the one by El Gamal multi-surface were used in open seas. And we took the same data, and with my former student, we did some 3D analysis. The red and black curves are from the Colorado study, and the green curve is by the study we did then, just to show that it's a reliable model. So we took that one, and then we moved to applications. And the first application was offshore wind. This is the very common offshore wind at the time, typically 5 megawatt model, like 80, 90 meter high to the hub, about 700-800 tons of weight, just to give you a feeling. And a typical wind load was applied, liquefiable. So the soil is the same used in the centrifuge box. And this is the model in FLAC 3D with the sunny sand 2004 model, not the further developments. Points inside and outside of the monopile were used to monitor the response. And and I'm going to show you some of the typical results from that study. This is the shaking. These are like 4 time steps, 4, 8, 12, and 16 were used. And these are excess pore pressure ratio with depth inside and just underside of the monopile. And it shows at 4 time steps, 4 seconds, 8 seconds, 12 seconds, and 16 seconds. These are at different points. What matters is one point to think, P4, which is inside, and basically any other point outside. It's interesting, P4 is the blue one. It is interesting is that realize that one is the full liquefaction, excess pore pressure with depth, and points inside basically gradually, quickly go towards liquefaction, whereas the point inside is less liquefiable all along. So as you can see, and this is like because of the confinement effect of the monopile. And this is the importance of thinking of this research in terms of doing a complete study, because the soil inside and outside have different features. While the points outside mostly are liquefying quickly, the point inside is hanging on and gradually comes up to liquefaction. And this is like several cases of tau gamma, shear stress versus shear strain at 2 points. One is inside S4 and one is outside S2, this one. And it shows that the point inside, the blue curve is for the first 6 seconds, red is the second 6 seconds to 12 seconds, and the dashed curve is the tau gamma in the last part when liquefaction is pretty much happening. And as you can see, the point inside is kind of doing some linear elastics about response until the last part of the shaking. Whereas if you look at the point outside, it quickly starts to liquefy because you have, in the initial phase, you have these butterfly, the dog bone banana form, and then it eventually goes into liquefaction, smaller cycles, and at the end, it is fully liquefied. So the model is nicely capturing the different part of the stress buildup and pore pressure buildup. Just to show you some sensitivity and effect of wind load, this is a summary of the results of this study that shows as a function of time how the displacement evolves. This is the horizontal displacement up to 60, 70. The horizontal at the seabed, of course, it is large because it is rotating. The base is rotating. And the vertical motion is like building up to 10, 15 centimeter. Is not dramatic, but of course, the most important thing is the buildup of the rotation, permanent tilt, which at the end of the shaking comes up to about 3 degrees, which is very large. The limit is 0.5 degrees. So even if it is not collapsing, this is at the end of the earthquake is not usable because the rotation is very large. What happens if there is a little less strong shaking, 0.12 G? The same feature is there. You see more horizontal displacement, but everything is smaller compared to the larger shaking. And the rotation is also smaller, but still above the limit. But the most interesting thing is that if there is no wind, no lateral force, very interesting feature is that basically it is, of course, sinking into the soil, vertical displacement, but no dramatic, pronounced horizontal displacement, nor any rotation. So it's sort of a rocking system sitting there back and forth. So that shows that this has been observed by other researchers. For manifolds and subsea structures, this is a very extreme example of a subsea structure on 4 caissons, but more common ones, smaller ones, could be, see the size of a person. It could be only on 1 caisson, on mud mats. But the main characteristic is that they are very chubby structures, large area and short structure. The height is small. So we looked at, in another study, at one of these manifold, not as big as this one, but more common one on a caisson. And we looked at the response in the same spirit as I showed for the offshore wind. And this is the same typical result. For subsea structures, there is usually not a large lateral load. So we end up, as a function of time, the rotation, which is the most important parameter, at the end of the earthquake, minor rotation, it simply sits there and rocks, even if it is even if, as this figure shows, the sinking is happening and there is a little horizontal displacement, this is as a function of time. You see, there is some, the dashed curve vertical displacement, there is a sinking, but it's not dramatic. And this study I was very interested in this to do it because during the time that I was very much involved in offshore structures, there was a lot of concern about subsea structures. What happens to them if liquefaction happens? Actually, these structures have large mud mats and foundation, and the net effect is some slight rotation. So maybe liquefaction is not as scary as it sounds. And it was interesting to study that if there is also a vertical shaking in addition, horizontal and vertical shaking, it's basically not much difference in the response. It's very interesting. Different shaking frequency. So the same, almost the same sinking, almost the same rotation, the same vertical rotation. Now, moving to the new development the last couple of years with the more developed version of memory surface version of sunny sand. I'm not going to spend any time on it because it is in the papers mentioned here, and it is in the several publications that you will see. It's based on the sunny sand 2004, bounding surface plasticity, critical state, and the same issues, but then memory surface hardening added. This is memory surface. Basically what it does, it tracks stress states that is already experienced, accounts for fabric changes and load-induced anisotropy. So it is basically more accurate in terms of, as you will see, and these are some references. Even if I'm not going to spend more than a couple of minutes on it, I thought to include it in the presentation in case this presentation will be shared after the event so that it has some slides for it. So this is like the elements of it. It has the memory surface, the yield surface, and the bounding surface. And this, what is happening is that the memory surface actually is moving, it is expanding, could shrink. The shrinkage is due to unstable fabric configuration, due to dilation. There is a translation, and there is, of course, the expansion. They are all capturing the different features of this model. So I move on quickly to some of engineering features of it. Improvement one of this model is that strain accumulation is more accurate in cyclic mobility. This is some experimental data that shows the accumulation of stresses and the way of axial strain. And in most existing bounding surface models, what is happening is that accumulation is basically symmetrical, whereas it is unsymmetrical in most existing, most common model. So the model that I'm talking about with memory surface is able to capture this feature more accurately. And the improvement number two is realistic pore water pressure accumulation. This is what you will get with the classical sunny sand from 2004. The rate is very fast. Liquefaction happens very quickly. And as you can see, experimental data shows the blue curve. It takes more number of load cycles until liquefaction happens. And this is what you will get with the advanced model. So basically, the memory surface version is able to predict the number of load cycles to trigger initial liquefaction and gradual decrease of mean effective stress, as you could see in these two figures, experimental versus this one, the memory surface version. It's relatively well capturing the development of pore pressure effective stresses. But then I quickly move to the last 10 minutes of my presentation on some applications I thought it is very interesting to look at what is the shear max, shear reduction with shear strain, the classical G over G max and damping. So this is what you would get. The blue curve is from Darandelli, and the black curve is what you would get with this sunny sand model, which shows that it has a stiffer response in the early part, but overall it is a good representation. But in my opinion, more importantly, is the damping. In earthquake application, damping is very important, and this is what you would get. This is what you would get with damping. The blue is again the Darandelli from experiment, and the black ones are what you would get from sunny sand MSU. And for different DR, basically correctly less than the classical experimental one due to undrained feature. And yeah, this is basically very encouraging. Some results for you for monopile response in undrained soil. So this is a classical monopile with typical 6 meter diameter. And I'm going to show you some figures with respect to how pore pressure is developed. The first, the one on the left side is mean effective stress ratio. So I will show you 3 slides. 3 cycles, 5 cycles, and 10 cycles. And on the right is the pore pressure evolution, again the same. So this is at 3 cycles. And as you could see, a wedge type liquefaction zone is how it is. And the shape is comparable with pore pressure distribution and high pressure. So this is 3 cycles. And as you could see, when we go to more cycles, it's actually more dramatic evolution, and at 10 cycles is full. If I have time at the end, I will show you also an animation, but it's basically the same thing. In terms of the same problem, in terms of what would be if we extract some PY curves, what would it look like? This is at a point, the one with the red one is at 2.5 meter depth, basically further down here, which shows the evolution of during these cycles, but still away from liquefaction. But a point close to the surface, the black one shows these typical banana shape liquefaction configuration forming up. So this is extracting the data from open seas and the model, and pretty encouraging. I skipped this one again, some more information as the evolution of the information for the record for those interested. And it is in the written version of the presentation. Effect of eccentricity and just a sensitivity as the load, because offshore wind, the load is further up. And as you can see, this is the effect. The figure here is the effect of, this is the effect of length of the monopile. And as the length is increased, linearly, there is a reduction in the displacement on the surface here. So as expected, as the length increases, there is more, there is less displacement, and this is the effect of eccentricity. As eccentricity increases, the load is higher and higher. You could see that there is again larger displacement as this curve. Again, surprisingly linear feature. Perhaps interesting is the PY. This result I like myself. Is that in offshore wind, at least with the level of vertical load involved, this shows the effect of a vertical load. It shows that if there is no vertical load versus there is these 2 curves with vertical load, basically the load, the displacement at the surface is not affected whether there is a load, vertical load or not. It's the 2 phenomena are kind of separate. And this shows the development of these PY curves with and without inclusion of vertical load. This is very interesting. That shows that one could separate them. And final example is for shaking, back to the same case I started the study of some 4 or 5 years ago, but with more modern monopiles, like diameter of 9 meters, depth of 20 meters, and the same shaking, pretty typical sizes of today. And what the focus here is what would happen if we use the models of 2004 versus the ones of with more advanced with memory surface. This shows the displacement on top, and this shows the rotation of the monopile. They are basically the same information, because the response on top is the rotation times height. So we could look at only one curve. This is as a function of time, and as the shaking continues, you will see that there is accumulation of rotation, and the two motions follow each other. But as expected, this is not a surprise, the models of 2004, they show more quick development of liquefaction, therefore larger rotation. So this is almost expected, but pretty much similar trend. And the corresponding, what happens if there is simultaneous horizontal load and not a horizontal load. If there is no horizontal load, a confirmation of what I said earlier. If this is again time shaking without any horizontal load, you can see that basically there is no rotation, almost no rotation, whereas with the wind load, there is accumulation of rotation. And finally, an example of manifold. In the earlier study, I looked at a case that the manifold was symmetric. And the observation was that it simply sinks a little bit and maybe not any rotation. So what we did in this study is that we took the same case actually, but then we changed the distribution of the mass, putting more mass on this side and less on this side. So, which is quite possible in subsea structures. And this is the difference between the two cases. Not much difference. This is on the left is when the two are similar weight, symmetrical, and the one on the right is when there is more weight, the same total weight, but more on the left side. It's not much difference on 20 seconds at the end in terms of total liquefaction. But when we look at development of the rotation, rotation is the most important thing. We will see that the one that is symmetric, M1 and M2 being similar, it's as expected, it's not doing much rotation, whereas as we change the mass distribution, it starts to have a preferred case, and then it starts to develop some rotation. And horizontal displacement, the two cases, it doesn't matter. The non-symmetricity doesn't do anything. Very little horizontal displacement. Finally, the summary and conclusion on the constitutive model. The MS version, memory surface undrained, improves the accuracy and yields realistic degradation curves and damping. I think this is for earthquake is very important. Earthquake response of wind turbines on monopiles, soil outside of pile accumulates higher pore pressure than compared to inside. Wind turbines might experience little rotation due to liquefaction if there is no wind and wave. Robust models can help us to do performance-based design. Earthquake response of subsea structures in terms of liquefaction is not expected to cause large permanent rotation of foundation if subsea structure has a symmetrical mass distribution. And features of cyclic response of monopiles is that a wedge-type liquefaction zone can be observed around the monopile, and vertical load has negligible effect on both pile lateral displacement and cyclic PY response. And with that, I'm very happy that you participated. Thank you for your attention.
Thank you, Professor Kaynia, for very interesting talk. And although now it's almost exactly on schedule, But because this is the last session, I mean today's last session, so we can still have some time to accept the several questions from our audience. So if you have any questions, you can raise your hand and our staff can let you speak your questions. So any questions or comments? Or you can type your questions in chat. So perhaps I have one question, Amir, for your simulation result about effect of lateral force. So can you elaborate on a little bit why, if we don't have the lateral force, actually we have a quite different response?
Yeah, basically, when you have the lateral load, you are creating the points on the loaded side, actually. You are imposing some shear stresses, and which bring them closer to failure, let's say. And once the shaking happens, these points more quickly go to, let's call it liquefaction or nonlinear response. So it's pretty much, if you think in terms of this simple block model response, that on slopes, that there is a preferred response direction. So once there is this lateral load, you are loading the side that is on the loaded side, of course. And when the shaking comes, the shaking itself is symmetrical generally, and it has a preferred direction of moving it in that direction. Therefore, this happens. It's a physical thing.
Okay, so you mean the lateral force when you do the simulation, and you apply this lateral force as a constant load rather than a time-dependent load?
Yes, usually these lateral loads, if they are also very dynamic, the situation is different. But these lateral loads, like wind has a major static component plus some turbulent component. And it is like has a large period. So once it is on the structure, it is almost like a static load. Wave almost the same. Current are completely similar. So even more worse, actually. So they are pretty much during the earthquake, they are almost, earthquake is like 10, 15, 20 seconds. They are almost constantly on the load, on the structure. So even if they are also dynamic with much lower frequency, so it appears as if it is a constant load there.
Okay, thank you. And perhaps another question, if we don't have, so I cannot see the question in the chat. So another question is about vertical loading effect. So normally we expect that there should be some effect from vertical loading if the structure is very tall, very flexible. So actually, this is the case of the offshore wind turbine on monopile. But from your simulation, it seems it's very interesting to note actually almost no any effect of vertical loading. So can you explain a little bit about this?
Yeah, this is actually at the time, 2 years back, I got interested in it, and I was surprised actually by another study, not this one. And we had to dig into it. And what I found out is that first, with offshore wind, the reason specifically for offshore wind is that weight is not a big factor actually, because they are, let's say, over-designed. They are far from capacity. So, but we, in another case, artificially increased the load, the vertical load, and still the effect was not dramatic. So we had to dig into it and found out that whereas vertical load is a very local phenomenon, very local, around the pile, even close to failure, lateral load is a more spread phenomenon. It engages larger soil around. So even if exactly around the pile is loaded to, let's say, if you're close to failure, if you look at the diameter of the monopile, especially monopile, it is a much larger area that will be helping the lateral response. So several studies we did, and this one confirmed that even when we got into the liquefaction stage, that vertical load is not very important, which is very good news actually for those who use PY and TZ curves, because then they could relax that they don't need to be interacting. That's the explanation I found. I couldn't find anything else, and it made sense when I thought about it.
Yes. Okay. Thank you. Now I see Professor Konto raised a hand. So please, do you have any comments or questions?
Thank you, Professor Yang. Amir, that was fantastic. Thank you very much. I was particularly impressed with the ability of the modified sunny sand model to capture so well the damping response, because that's not an inherent characteristic of this class of models. They actually usually overestimate the damping. So I was wondering whether you could give us some guidance on that. Is a particular calibration process, is an inherent characteristic of the model that achieves, because particularly for these deep deposits can be really, really crucial to get the damping right.
Yeah, thank you. That's a very good question. I always wondered myself, when we started this study, as a classical geotechnical earthquake engineer, as you said, I'm also interested in this thing, what a model does. And I always ask constitutive modelers, how does your model perform with respect to G over G max and damping? And so when we did that, I was crossing fingers that it does well. And it just so happened that it did well. I don't have any explanation. No calibration was done. But it is built into the feature that as soon as pore pressure comes into the picture, then this facade, this feature of the response, like this banana shape happens. This helps. If you are in the linear range of these models, low values, then they start to be, as you said, like larger damping than experiment. But once you come to this range, they start to go into this shape, and without really manipulating anything, it's just a blessing that they start to do well. And they even give lower damping. This is because of the shape of this, as you remember, the PY and the banana shape, and they give lower damping. So no, it's a blessing that it happens. Probably you would see the same thing in not even the more advanced MSU version, even probably if we didn't do that, even with the 2004. However, you should come to large strains so that it has started to have this new feature of the response.
Maybe then maybe I didn't capture, maybe I didn't see then very well the whole range, because I thought you showed it for the entire range.
No, it was not absolutely, but of course the low range maybe is not of much concern. So it was further from the
the concern with the lower range is when you have a deep deposit and you have to basically propagate through lower strains to higher strains, and then it can overdump.
Yeah, no, but honestly, yeah. So as you can see, if I really start to stretch it back, although it is, as you say, it's correctly, it is already very low. But this is a feature that actually these models, I can say, even without having a number for it, even 2004 probably will have this simply. But that one even more maybe, because it quickly goes into liquefaction. But as you can see, this is going to maybe going to cross these data. So no, it's don't want to take credit for that. It's it's pure luck.
Thank you.
Okay, thank you. So here I see another question, but it's related to damping. So I believe the audience, Oza, right? So it should be okay to you. And so I think we have to stop here. And thank you again, Professor Kaynia, for a fantastic lecture. And
thank you very much.